Gloria, Gloria. Hey there. So we're looking at electric potential example number 5 here. And we're going to find the electric potential given by a point charge this time. So how rude. What's the electric potential at a point 0.5 meters away from a 15 microcoulomb charge? And then we're going to do this again for a negative 15 microcoulomb. So here's our positive 15 microcoulomb charge. So that's times 10 to the negative 6th coulombs. And we are just, whoop, 0.5 meters away. It could be in any direction in 3D spherical space. Doesn't matter because this is our R value here. And if we would like to find ourselves a potential here, a voltage, well, that voltage for a point charge is just going to be KQ over R. That's it. That's all I got here. So K is 9 times 10 to the 9th. That's Coulomb's constant. Q is our 15 times 10 to the minus 6th divided by our R, which is 0.5. And if we throw all that together into the magic of a calculator, we're going to get an answer here of about 2.7 times 10 to the 5th volts. And there we have it. That is our electrical potential some distance away from a point charge. Notice that I did leave this as positive. Okay. If we want to do this for a negative 15 microcoulomb charge, well, we do the same thing, except this time, instead of it being positive 15, we're just going to say it is negative 15 times 10 to the negative 6th. And the equation is the exact same. We're still going to have KQ over R here. So it's going to be 9 times 10 to the 9th. I will put in the negative here. If you've been following along with the videos, you might be like, wait a second. Every time he does this with forces or electric fields, you say ignore the negative charge and draw a picture. Why aren't you doing that now? Well, electric potentials, voltages, are scalars. I don't care about the direction. It doesn't matter. All that matters is the magnitude of this. And because of this, I didn't need to draw, a fancy picture here saying like, oh, it's pointing to the left, it's pointing to the right. It's not. It just is what it is at that point in space. So we're actually going to get the same potential, but just a negative, 2.7 times 10 to the 5th volts. And a kind of neat thing about this is if we had this positive 15 microcoulomb charge and we had a negative 15 microcoulomb charge, and we wanted the potential directly between them, what would it be? Well, it would be 0. It would be positive from the first one, and then we'd add it to the negative of the second one. It would be a 0 potential right there. Would there be an electric field? You bet. Electric fields go from positives to negatives. And this makes sense because if we were to put in a small positive test charge, it would move along that electric field line. It'd be repelled from the positive side and it'd be attracted thanks to the negative side there. But that is for electric fields. When we're talking about potentials, they are scalars. We do indeed put in the positive and negatives here. And then we just add them up. So it's a lot easier. It's way easier to solve complicated, geometry problems with vectors or with these voltages here, wrong V, because they are scalars. You just add them up. So much easier, much straightforward, and it's a lot more fun, in my opinion, to play with them. So with that, this is finished. Take it easy. Adios.